Alright, so now let's prove the first variation formula. First, for simplicity, let us just assume that the whole curve, gamma, is regular. So why can we assume that? Because we can always chop this integral up into integral from a0 to a1, a1 to a2. On each of these p's, the curve is regular. So if we can prove the formula for the regular case, then we can just add up the formula in each of these cases to get this general formula. So let us just assume that gamma itself is regular, in which case we can replace this term here by this term, only involving b and a. Now, before starting with the curve, let us recall some terminology. So remember, we have two special vector fields along gamma. The first one is the vector field along the main curves. We denoted it by t, right? This is defined to be, and so it captures the change of gamma in the t direction. The other vector field is along the transverse curve. So S capture the change of gamma in this S direction, right? And observe that S0 is just the variation field of gamma. And what is T0? Well, T0 would just be the velocity vector field of this little gamma. Alright, so now let's start the proof. Let's start from the left hand side here. So this length of this gamma s, this curve gamma s, by definition should be the integral of its the magnitude of its velocity vector, right? But its velocity vector is just this t. So really this is the integral of t. Now, because this is smooth and the domain is compact, we can switch this integration and differentiation. And now what's this derivative? So here first we use chain rule. So this should be the derivative of this expression with respect to this inner product. So we get this, right? But then we have to multiply with the derivative of this inner product with respect to partial s. How do we differentiate this? Well, we can differentiate this using this product formula. Remember, we are talking about the connection that we're using is the Riemannian connection, and it was supposed to be compatible with the Riemannian metric. And recall that compatibility is equivalent to the following product rule. So if v and w are two vector fields along the same curve, then we have this differentiation rule. So here we view this t as a vector field along the transverse curve. Alright, so from that we see that then this part, this expression is equal to this. So this whole integral is just going to be integral of this expression divided by this is just the norm of t. But now we have the following symmetry. So this is going to be equal to this from the symmetry lemma, and this comes from the symmetry of the Riemannian connection. Remember, we require the Riemannian connection to satisfy two things. First, it must be compatible with the Riemannian metric, but secondly, it must be symmetric, i.e. its torsion tensor must be 0. So that symmetry leads to this symmetry lemma, which allows us to rewrite this dst as dts. What this lemma is saying is that the change of this vector field t, right, this velocity vector field t in the s direction is the same as the change of this velocity vector field s in the t direction. Okay, so now that we have established this identity, we can plug in s equals to 0. We evaluate this at s equals to 0. Now at s equals to 0, this t is just going to be the velocity vector field of the curve gamma. But remember, this curve gamma was assumed to have unit speed, right? So that means that this norm, this magnitude must be 1. Great, and so here again we replace this t with a gamma dot because it's just the velocity vector field of gamma when s is equal to 0. Now when s is 0, this big S, right, s of 0t, that's just gonna be this variation field. So we replace this dts with the variation field. And now again we use this formula, this compatibility formula, to rewrite this as the following. And now it's simple because we can just use the fundamental theorem of calculus to integrate this derivative, right? And so we get this expression which accounts for the second term, and we have this expression which is the first term here. Sorry, I must have gotten some sign incorrect. It should be minus, but those are just minor details. The key here is to see that we use two main property of the Riemannian connection. The fact that it's compatible with the Riemannian metric, and the second thing was that it's symmetric. Alright, so that's the first variation formula. Next, we'll discuss how this implies that length minimizing curves must be geodesics.